a result from Shift2RailCONNECTA with Carsten Pfeffer from Alstom. So welcome.
This is not the correct presentation. Number 19. Yeah. So I'm Carsten Pfeffer. I'm working for Alstom, formerly working for Bombardier. And I've participated in the Shift2RailCONNECTA project. And I want to tell you something about one of the results, which is the specification of the simulation and virtualization framework. First, some things on past and present testing. It is testing on real trains, and this is quite expensive. It is sometimes quite dangerous. Why? Because you need a train, you need a track, you need an operator, so it's quite time consuming. You have high power stuff you need. You have quite high speeds. Sometimes you have noise and so on. And it's sometimes quite critical. For example, if the brakes do not function correctly, then it's not fun to test it. Also, testing on real trains is not complete and not deterministic. For example, you cannot test everything like broken cabling or something, or for example broken or not working brakes, and you cannot reproduce tests correctly with the same preconditions, with the same timing, for example. And also testing on real trains is getting more complex due to the huge amount of software that is on the trains currently. And of course, on trains also you have a limited support for automation, for continuous integration and testing. One goal of Connecta was then to get some further steps to the virtual testing and virtual homologation, and the result is a full specification of the simulation and virtualization framework, which is then supporting the test automation on all levels, which is supporting tests in laboratory environments or also in software in the loop environments. And this is then providing left shift of all the tests, providing early feedback to software developers and so on, and so saving time, saving costs and so on. The first thing that is defined is to specify a simulation execution environment with all the communication protocols we need to combine all these components. We have some tools based on the PC for management, for configuration, and we also have a hardware in the loop interface, which we need to again trigger or stimulate hardware devices. The first is the software tool set. This is planned to run on the PC, on the tester's PC. It contains a configuration tool which is needed for the network parameters, for the telegrams, data signals, and so on. We have a monitoring signal which is defining which part of the data we want to monitor, we want to measure, like signal values, like the state of the simulations, and so on. And we have a test automation tool which is used to evaluate tests, to run tests, and also to maybe replan tests that have failed in a previous stage. Then the simulation host is part of the simulation framework. This is handling the basic communication levels. This means that it provides some high-level data signals later for the simulations, for example. It has management signals for powering simulated devices and so on. And it also supports fault injection into communication layers, for example. It is then also available to have some antivirus and electromechanical simulations running on that simulation host. The simulation host will also control the hardware-in-the-loop interfaces, so the physical interface to real devices. And it should also communicate to other instances of the simulation host for distributed testing or for co-simulation stuff. Then let's talk about the device simulations. The first thing we have is end-device simulations. It's a logical scope, a simulation of an end device communicating over a network. It's a quite simple API. We have a setup and a cleanup method. We have a start, stop, reset methods. We have a read inputs, write outputs, and some processing stuff. And the interface to all the rest, to the communication and also to other simulations, is a signal-based interface. So it's kind of a high-level interface on data signal level. So such a simulation doesn't need to handle communication layers like a safety layer version 2, for example. So it's more easy to implement and to maintain those simulations. And we have, sorry, one back again. And we have a dynamic approach here, so that we have the possibility to exchange a real system by a simulation at runtime without a need of reconfiguring all that stuff. The hardware in the loop is needed since if you look at the upper image here, we have an electromechanical environment to the real end devices, like speed sensors providing just an electrical signal, like temperature sensors using the outside temperature, for example, or pressure sensors or whatever. And if you want to replace that by a simulation, then we of course need a way to still trigger the inputs of those still real devices. And for this we have the hardware in the loop interface that can then provide electrical stimulating signals to the real devices of the SUT. The next thing is the co-simulation and distributed test setup. So co-simulation means we designed one simulation host for one consist. So if we have a multi-consist setup, then we need several instances of the simulation host, which need to be synchronized, for example, for the train speed. And simulation distribution means that it should be possible to distribute the test setup to different test sites, for example, for load balancing, or for example, for providing specific test means like a climatic chamber for different for specific parts of the test setup, and some other things that can be located in the developer of the TCMS, for example. The software in the loop is more or less the fully virtualized environment then running on the developer's PC. So we have support of running a complete train on the developer's PC, which also enables then for cloud testing, also for continuous integration, continuous testing, fully automated. We have synchronized the components here with a simulated real-time environment. This also then supporting slowing down the complete system, and also for speeding up. Slowing down is required, for example, for debugging. If you have a developer that is stopping one of his simulated applications, then of course all the rest of the simulation should also stop. And speeding up is quite interesting for long-lasting tests like preconditioning, for example. And the end-device emulation is then kind of emulation of the real environment for the to be able to run the complete real software on such an emulated device, which is then a step towards a virtual homologation, so that we can use those results for homologation process. Thank you for the audience.